My devotional episode. Work out for a while, come back.
All right. I will. Wait a minute.
What's going on here?
Oh no, I thought my mic not turned in. All right, let me begin. Dearly Father, we thank you for this day. I thank you again for the students. Just ask you to guide our work today and just help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. So I guess I should get into the limit laws. Sequential limit laws. I won't write all of them. I'm just going to write the one that's most important to us at the moment, which is this. Well, two of them really. The limit as n goes to infinity of a sub n plus b sub n is equal to the limit as n goes to infinity of a sub n plus the limit as n goes to infinity of b sub n. And two, if c is a real number, then the limit as n goes to infinity of c times a to the n, is equal to c times the limit as n goes to infinity of a sub n. And this is assuming, so provided, the limit as n goes to infinity of a sub n, let's say, is equal to big A, and the limit as n goes to infinity of b sub n, let's say, is equal to big B, where a and b are real numbers. Now, I also projected two other limit laws last time, that the limit of a product of two sequences is the product of the limits, and that the limit of a quotient of two sequences is the quotient of the limits, provided that those limits exist and are. And for the division one, you have to have non-zero terms, but I won't prove those in class because the proof of those is actually kind of, well, hard. But this one is not too hard, and also it's one of your homework problems, so I probably should do it, right? Okay, so let's look at the proof. How do we prove this? So I'm just going to do it. Let's let epsilon be greater than 0, and choose n sub a and n sub b elements of the natural numbers for which n greater than n sub a, well, implies the absolute value of a sub n minus a is less than, let's say, epsilon over 2, and n greater than n sub b implies that the absolute value of b sub n minus b is less than epsilon over 2. I can make these choices because I'm assuming the limits exist, right? And so if the limit of the sequence a sub n and the limit of the sequence b sub n exists, that means that I can go far enough out in the index n for each to make the distance from the points in the sequence and the limiting values as small as I like. So in particular, I can make it as small as epsilon over 2. Now, why would I choose epsilon over 2? All right, well, check this out. Let big N equal to the maximum of n sub a and n sub b, right? Then for n greater than big sub n, we have the following. If we look at the absolute value of a sub n plus b sub n, all right, a sub n plus b sub n minus parentheses a plus b, what is that equal to? Well, just make an algebra step here. That's equal to the absolute value of a sub n minus a, right, plus the absolute value, plus b sub n minus b. So I just distributed, just plain old algebra step there, right? Now, the thing is, there's something called the triangle inequality, right? There's a triangle inequality for the absolute value function, which is critical to these kinds of arguments. And so we can argue that this is less than or equal to the absolute value of a sub n minus a plus the absolute value of b sub n minus b. All right? So this is by the triangle inequality. But let me ask you a question. We've assumed that n is the maximum of n sub a and n sub b, right? What does that mean? Think about this. That gives you two things, right? So if this is the case, what do we have? We have what? We have n is greater than or equal to n sub a, and n is greater than or equal to n sub b, right? Which means what? We have both this condition here, right? And this condition here. So this is less than epsilon over 2 plus epsilon over 2, which, by the way, is equal to epsilon. So what have I shown? I've shown that you can go far enough out in the sequence of a sub n plus b sub n so that we can make the distance from the point in the sequence arbitrarily close to a plus b. This proves, then, that I'll put it up here. Thus, the limit as n goes to infinity of a sub n plus b sub n is equal to a plus b, right? But what is a and what is b? It's exactly the limit as n goes to infinity of a sub n and the limit n goes to infinity of b sub n, which is what we're trying to prove. That this proves 1. Now, to prove 2, yep.
So you went from less than equal to less than. Is there a reason equal to that dropped?
Yeah, because I'm using this here and that here, which are strict inequalities.
Okay.
So it's not equal. It's not equal to the line above. It's strictly larger than that. Mm-hmm. Now, to prove 2, yep.
I think you already explained this like yesterday. What does a sub or n sub a represent? Like, what is that representing?
These are natural numbers.
Yeah.
I can choose them because we're given that the limit as a sub n equals a, which means it's a convergent. So I'm assuming that a is a real number. This is a convergent sequence. What does that mean? That means I can choose integer large enough to make the difference between a sub n and a, the absolute value of that difference, as small as I like. So in particular, I can make it less than epsilon over 2. I'm just choosing n sub a to make that happen. And the same for n sub b. So they're integers which are given to me from the definition of convergent sequence. How would I prove 2? Well, the proof of 2 needs 2 cases. I mean, the proof of 2 needs 2 cases. There's a stupid case which we can deal with quickly. For 2, if c equals to 0, then ca to the n is equal to what? It's equal to 0, right? And so in that case, you have the limit of the 0 sequence, right? And what's the limit of the 0 sequence? It's just 0, right? But that's also equal to 0 times the limit as n goes to infinity of a sub n. So, okay, so number 2 is true in the case that the absolute value, excuse me, in the case that c is equal to 0. It's true, right? Here you go. Oh, need a pen or something? Or yeah. Okay, so let's look at the case c not equal to 0. What's my goal? I want to show that ca sub n minus c times big A is less than epsilon, right? So what I'm going to do is I'm going to let epsilon be greater than 0. I'm going to choose n sub a in the natural numbers such that for n greater than n sub a, we have the absolute value of a sub n minus a is less than, epsilon over the absolute value of c. I can do that because the absolute value of c is positive. Oh, thanks. I didn't see you come in. Wait a minute. Yeah, that's right. Where's Austin?
Oh.
Oh no. Are you gonna live up? Are you gonna live up to Austin's? Are you gonna live up to the?
I'll supersede.
You supersede. You're gonna supersede it. I like it. I like it. I like it. Take no prisoners. Very good. Very good. So that's what we're gonna assume, right? So then consider the absolute value of c times a sub n minus c times big A is equal to the absolute value of c times the difference of a n and a. All right, which then by properties of absolute value is equal to the absolute value of c times the absolute value of a sub n minus a. All right. And what did we assumed that that was what, less than epsilon over the absolute value of c, which is what? So we get less than absolute value of c over times c over absolute value of c, which is of course equal to epsilon. Thus, the limit as n goes to infinity of c times a to the n is equal to c times the limit as n goes to infinity of a sub n. And so there you go. There's a proof of 1 and 2. So these, I don't ask you to be able to prove everything in here, but these are two that I'd like you to be able to prove. All right. So to reflect that wish, I made these homework problems. You might say, you mean to tell me that you're just writing out the solution to my homework problem in class? Yes. Yes, I am. Now I want you to write it down. And then I want you to understand it, all right, in the process of that. Yeah.
What's the at the end?
Oh, that just means that I just write that when I'm done.
Oh.
End of story. In the notes, I usually put like this. That means end of proof, if you look at my notes. Other people put QED, but I think that's kind of pretentious, so I don't do it. I don't know. Which is some kind of Latin, I don't know, right? But okay, so some of you have a classical Christian education. You might know what it means. Let's see here. Okay, so moving on here. We have the squeeze theorem. So what's the squeeze theorem? This one I won't prove. I'll just state it for you. Suppose sequences, you got your a sub n, b sub n, and c sub n have bn less than or equal to an less than or equal to cn for all n greater than m. All right? And let's also suppose that the limit as n goes to infinity of b sub n is equal to the limit as n goes to infinity of c sub n. All right? Then what's the punchline here? Oh, let me, because I'm really tired of writing that, let me just call this thing L. All right, then the limit of the middle sequence, the one that's sandwiched in between, right? The limit as n goes to infinity of a sub n is also equal to L. So this is the squeeze theorem. There's a whole class of problems that, like, the squeeze theorem is kind of like our only way to calculate the limit, right? It's lovely when we can use L'Hopital's rules, like the L'Hopital rule, and like borrow from like the calculus of a continuous variable. But man, there's just some examples which you've got to use a squeeze theorem for. All right. So here's one. First example. Check this out. If the limit as n goes to infinity, all right, of the absolute value of a sub n is equal to 0, then what can we say? Let's fill in that blank, all right? What can we say? Check this out. So can you guys tell me what goes before and after a sub n? Let me ask a more leading question. If a sub n is positive, the absolute value of a sub n goes on what side of that? I mean, this is always true. The absolute value of a sub n is always larger than or equal to a sub n, right? That's true whether or not a sub n is negative. Right? If a sub n is negative, that's a strict inequality. Yeah? Now, if a sub n is positive, then this is an equality, right? But on the other side of this, you have this, yeah? You might not have thought of this before, but it's not a terribly deep thing I'm saying, right? Try it out for some numbers, you'll see it's true, right? Okay, so we're assuming the limit of the absolute value of a sub n is equal to 0, right? Then what? So we know this one is going to 0. So we can think of this as being like quote-unquote b sub n, right? Think of this as being the quote-unquote c sub n. And they're both doing what? They're both going to 0, right? So by the squeeze theorem, we have the limit as n goes to infinity of a sub n is equal to 0. In other words, if the absolute value of the sequence converges to 0, then the sequence must also converge to 0. So I can fill in the blank there. Punchline here is this. Now, here's something sometimes cautionary tale, right? If the limit as n goes to infinity of like the absolute value of a sub n equals to 2, it does not imply the limit as n goes to infinity of a sub n is equal to 2, right? Yeah.
But you could say that the absolute value is the limit of a sub n equal to 2, right?
Nope, can't say that either. I don't even know the limit of a sub n exists. For example, if we do a sub n equals minus 2 to the n, the absolute value of this is just equal to, I don't want 2 to the n, I want 2 to, my bad. I wanted minus 1 to the n times 2. That's what I was looking for. Sorry about that. So minus 1 to the n times 2, right? The absolute value of that is what? It's 2. But what's the limit of this? The limit of that doesn't exist. It has one subsequence, which is 2, 2, 2, 2, 2, 2. It has another subsequence, which is minus 2, minus 2, minus 2, minus 2, minus 2. So those converge to 2 and minus 2 separately. And this sequence diverges due to oscillation. 0 is special in this regard. Okay, this example 1 is only good for 0. So just don't make it say more than it does, is all I'm saying. Okay. Next example, 3. The limit as n goes to infinity, I'm just going to tell you the takeaway message here, and then I'll explain why this is true, of r to the n, it's 0, all right, if the absolute value of r is less than 1. It's 1 if r is equal to 1. It's infinity if r is greater than 1. And it does not exist due to oscillation if r is less than or equal to minus 1. All right? Now, we proved part of this last time, right? Do you remember? We proved this we using the bounded monotonic sequence theorem. It was my first example after that. We proved it in the case that, like last time I dealt with, I did 0 less than r less than 1, and I showed that the limit as n goes to infinity of r to the n is equal to 0 in that case. Actually, I put a c in front of it last time and made it slightly uglier. But put c equal to 1, okay? So what if r equals to 0? Well, that's a kind of a dumb case, isn't it? R equal to 0, you have r to the n the sequence is what? I guess it's 1, 0, 0, 0, so forth and so on, right? What's the limit of that sequence? We don't need anything fancy for this one, right? The limit of that is 0, right? On the other hand, if we have -1 is less than r is less than 0, yeah? Then what do you have? Notice that the absolute value of r is equal to what? If r is negative, what's the absolute value of r equal to? In the case of negative, the absolute value is minus the input, right? It's minus r. And that fits into the case we did last time, right? Thus, the limit as n goes to infinity of the absolute value of r to the n, I'll come back to your question in just a second, is equal to the limit as n goes to infinity of minus r to the n, which is equal to 0 by what we did last time. So therefore, the absolute value of the sequence converges to 0, which then implies that the limit as n goes to infinity of the sequence converges to 0 as well, using example 1. Yeah, what was your question?
How do you have 1 if r is 0?
Oh, 0 to the 0 is 1. So if you want, you can make it 0. I think we take it to be 1, but yeah. There's a debate about this. So, yeah.
For the stuff, the absolute value of r is equal to negative r, we're using the first part of the, not the 0, but the twice part.
I'm using this assumption right here. So I'm assuming that r is negative and between -1 and 0. If that's the case, the absolute value is equal to minus what you're taking the absolute value of. But then that means that if I look at the absolute value of the sequence, I really am looking at minus r to the n. And as such, I proved that as 0 last time, but then by example 1 again, we get this as 0. The rest of the claim follows by just kind of like duh. Like if this one here, right? If it's 1, what do you got? Limit as n goes to infinity of what? Of 1 to the power n, which is just what? That's just 1, right? Because you're taking the limit of the constant sequence 1, so that limits to 1. And then in the other case, if you have r is either, let's see here. I think I wrote that down wrong. Oh, r greater than 1, my bad. So either one of these cases, right? Well, certainly if r is greater than 1, what can you tell me about? If r is greater than 1, what can you tell me about our words? R to the n is what? If r is greater than 1, r to the n is unbounded, isn't it? And if it's unbounded, we proved last time that it can't be convergent, right? So it's unbounded. And likewise, this one is unbounded, right? If it's less than, well, excuse me, if it's less than or equal to -1, if the -1 case, we've dealt with that before. That's the -1 to the n. That was an example we proved before. Didn't exist because it had the 1 sequence and the -1 subsequence. That one doesn't exist. And then if r is less than -1, again, it's an unbounded sequence, therefore it's not convergent. So anyway, there's a lot of cases, but this is the takeaway message. You need to remember this result for your future calculational purposes. That's why I'm making a kind of big deal out of it. Yeah.
But can you explain again how you went from -1 is less than r is less than 0? Why that is the absolute value of r is negative r?
Well,
Why is that true?
what is the absolute value function? So like absolute value of x is equal to minus x if x is less than 0, and it's x if x is greater than or equal to 0. And you might say, no, you're wrong. It's the square root of x squared. And we would agree. That's the same formula also. So, because square root is by definition non-negative. Okay, so that's that. Now let's look at one that's actually interesting. Okay, so this one's actually a little bit more challenging in terms of just calculation. So up to this point today, I've been sharing with you things that we need for future purposes, but you know, I don't think the last example is particularly surprising, right? I think if you really stop and think about what I claimed there, you would know it without ever having darkened the doorstep of the bounded monotonic sequence theorem or some of the other things we proved, right? These are really kind of intuitive claims. This one here, this one starts to get interesting in terms of maybe there's some, it's not entirely intuitive until you gain more intuition at least. So here's example, where am I, 4? Check this one out. So we've got a sub n equals 5 to the n over n factorial. So I'm going to show you the trick. Basically, it's this. Suppose n is, let's, for the sake of our convenience, greater than or equal to 6. And then you can do this. 0 is less than or equal to 5 to the n over n factorial, right? Fine. But then what? Well, this is equal to 5 times 5 times 5. We'll be here all day, yeah? 5 divided by n times n minus 1 times n minus 2, all the way until you get down here to 1, right? So, let's see here. Oh man, I chose poorly. I got to write more, guys. Sorry about that. 5, 5, 5. So let me put 5 here. 4, 3, 2, 1, like that. Okay. So I wrote it the opposite. I wrote these factors the opposite order in my notes. It's messing with my head for a second here. I guess if I just followed my notes, we'd be in less trouble. There's no trouble yet. So my question then is, what can I do with all of these numbers? Well, let's say not all these numbers, but all these numbers. How can I make this fraction larger in a way which is convenient to us? So I'm going to leave the 5 over n as it stands, okay? I'm going to leave that there. I want to put something in here that's different. And I'm going to leave this over here. We have 5 to the 4th. This is 4 factorial, right? So what about n minus 2, n minus 1, n minus 2? See this here? This means n minus 1 is what? Greater than or equal to 5, right? What's that tell me? I'm not sure I believe my notes. All right, let me think about this here. We've got I want to make the fraction larger, right? Can I replace those with 5? Each one of them, can I replace with 5? Is that reasonable? No. That's not reasonable because assuming n is greater than, n minus 1 is greater than 5. Oh, yeah, I'm an idiot. So 5 is, you guys, I'm a dummy. Look, 5 is less than or equal to n minus 1, is that right? That's not what I want. What have I done? Wait. Every so often, my brain just flips a switch with inequalities. We have to unflip it.
You said what? You said greater than, but you're not less than. That's
Yeah. Okay, but well, n is greater than 5. N minus 1 is greater than 5. No, I need an inequality for n larger than 6. I'm sorry I'm getting hung up on this, guys. It's not complicated.
Just take our position.
in the test. And the test. And the exam.
Let's see here.
Not do it.
The class in general.
Yeah. Should learn it. It's bad math.
Okay, yeah, I've got this twisted. All right, so
Thank you, sir. Very much appreciated. Just want to make sure you have it. It's more than that.
sorry, guys, I have a mental block on this one at the moment. Let me go on to the next one, which is the same problem, but in general. This one will work better. Maybe, I think in the process of doing the next example, I'll figure out what to fix there. So I tricked myself into the step being reasonable, but it's the opposite of what I need. So that's the problem. Okay, so here, the next example, we will fix it. So here, we'll look at r to the n over n factorial, all right? And notice that there exists integer m, positive integer, such that m is less than or equal to r is less than m plus 1. Now that's a sneaky step right there.
Can you explain that again? Sorry.
Give me a number, any number.
7.
Make it 7.3.
Sure.
M is 7, m plus 1 is 8. There you go.
Okay.
Give me another number.
253.1.
This is 253, this is 254. So yeah, I mean this is, I think this is called the Archimedean principal property if you take real analysis, but who cares, right? I mean it's obvious. If you look at the decimal expansion of a number, r, you can always find numbers before and after. Now, I guess I am assuming what? R is positive, right? Okay, so we have that. Now, this will go better, promise. 0 is less than or equal to r to the n over n factorial, all right? And, I mean, it's not actually equals, but it's less than, or it's actually strictly less than, but we can throw the equals in there if you want. And if you look at that, we have r times r, dot, 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 times r over 1 over 2 over m, all right? And then we have r over m plus 1, r over m plus 2, dot, 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 r over n. Now, looking at this, right, if n is greater than big M, greater than or equal to big M, right? What can you tell me? Now what do we got? Now we're in the situation, well, I guess, now we're in the situation here that can you tell me, let's see here, if that's the case, where does n fit into this story? Yeah, I should make this strict. Let me make that strict just to be safe. See, then r is what? If r is less than m plus 1, right? Then, let me write that. N plus 1 is greater than m plus 1, right? In other words, m plus 1 is what? Is less than n plus 1. In other words, m is what? Getting to the point here. M is less than n. I still haven't, I'm sorry guys, let me stop writing. What I wrote in blue is not helpful. So my point, if I could get to it, is that what can we say about these factors here? If r is less than m plus 1, what can you say about this factor? Right? And if that's less than 1, then guess what? So is this, right? And on down the line, right? These are all less than 1. It's a product of factors less than 1, right? Oh, I know what I'm doing wrong. I'm a victim of my own typesetting. I should have made my curly brackets stop like right here. I wanted to see if I need to leave this last one out, right? I definitely can leave the last one out. Leave the last one out here. What's the last one? N minus 1, right? So right before that would be r over n minus 1, and then you have r over n, the last one. So let's be there, right? So is n minus 1? We should be able to argue that r over n minus 1 is less than 1. Can we see that? So those are all less than 1. We've got that r over n over here. Whatever this is, I don't really care. It's just a number, right? So you can call this thing c. All right? And then, now that we've done all that, this is less than or equal to c r over n. Then what? What happens as n goes to infinity here? So yeah, this goes to 0 as n goes to infinity, yeah? What happens with the 0 sequence as n goes to infinity? Also goes to 0, right? Therefore, by squeeze theorem, what do we get? the limit as n goes to infinity of r to the n over n factorial is equal to 0 for any positive r. Now, I think we can come back to here and repair it now, right? What should I have made my m? Like, if you understand this, we can go back and do this one carefully now, right? How would we fix it? I would choose m equals to 5, right? So, like, basically, think about m equals to 5. And look at n greater than 5, I think, is the construction, right? And so we'd have what? We have 5 times 5 times 5. 5. And let's see here. If I follow the same argument, I do my 1 times 2, go up, not down, all the way up to what? All the way up to 5. And then past that I have what?
Over 6.
Yeah, 5, thank you. Put me out of my misery. I appreciate that. Let's hear. 5 to 6, 5 to 7, 5 over what? N minus 1, 5 over n, right? And this is less than or equal to, this is 5 factorial. Excuse me, that's not 5 factorial. That's 5 to the n, 5 to the 5 rather, over 5 factorial, which you could simplify, right? And this is collectively terms less than 1, right? Less than 1, less than 1, less than 1, because n is greater than 5. That makes this less than 1. Or equal to 1, I suppose. If it's 6, this is equal to 1, right? Fine. So less than or equal to 1. And then we're left with the 5 over n. So again, what happens? This goes to 0 as n goes to infinity. Therefore, by squeeze theorem, right? How about this? Example 6. This one's not in the notes, but it just occurred to me. How about the limit as n goes to infinity of minus 5 to the n over n factorial? What would you do with that? I would just say, notice, the absolute value of minus 5 to the n over n factorial is equal to what? It's equal to 5 to the n over n factorial, right? Which goes to 0. So therefore, the limit as n goes to infinity of minus 5 to the n over n factorial is also equal to 0. So we can extend example 5 to negative values using the absolute value goes to 0 implies the sequence goes to 0 theorem. All right? All right, so let me just project the last, yep.
So how do you what happens to the second term? Like the 5 to the n over factorial, then what happens to the over 7?
This is less than or equal to. These are all less than 1 or equal to 1. So that just
goes away.
I replace this by 1 that's larger than this.
Okay.
So, yeah, squeeze theorem. Yep.
Could you just quickly go through the terms, like different e's and backward e's?
The what? The
Backward e.
Oh, yeah, sure. So this means there exists versus this one, which means for all. Other things I tend to write is this, which means such that. I'm sure there are other abbreviations I use without thinking, but those are the big ones. Uh-huh. So pretty much those are the big things I wanted to tell you about sequences. There's a few more examples I'd like to look at with you. And we'll be done for today, if I can get to my examples. I will just describe what happens past this point, the ones I haven't gotten to here at the moment. Oh, there it is. The ones I haven't showed you yet, I'm using L'Hopital's rule and borrowing from like limits at infinity well, hopefully you saw in Calculus 1. If you didn't, well, I'm sorry, but then you need to look at some of those. And if you email me, I can recommend where to look in Stewart and stuff like that. 2.6, there we go. Sorry, I got hung up on that silly problem today. It ruined my flow. Let's see here. Sorry about that. You know, this stuff is hard. It's still hard for me. All right, so obviously at the moment, I would point out that, where'd it go? Example 1.27 is currently incorrect. I need to edit that and fix it, okay? So if you printed it out already, then beware. Put an X through 1.27, it needs to be fixed. I will fix it. I mean, the fix of it's on the board right now, but I need to fix it in the notes. So theorem 1.29 is a really nice theorem. It says that if you've got a continuous function and your limit, the value of the limit goes to where the function is continuous, then you can pass the limit inside the function. Oh, you already got it. Man, you're on the ball. Yeah, wow. Fancy pants. Let's see here. So then, so this is super useful because, for example, since sine is continuous, I can take the limit of the sine of this sequence, and I can do, well, it's sine of the limit. And, well, this sequence is not obvious because that's infinity minus infinity, right? So how do you deal with that? Well, use properties of logs, then do algebra, and then, well, that's log of 2. Once I know that that limit exists, it's log 2, I just put it back in there. That's it, right? So not everything has to be some, like, conniving squeeze theorem argument, right? We can also do arguments that are similar to the ones hopefully we saw in Calculus 1, right? Here's another one. The exponential function's everywhere continuous. That's super nice because I can pass the limit inside, and we know that the limit of the hyperbolic tangent's 1, right? Because of this algebra down here, hyperbolic tangent, remember, simplifies by dividing through by e to the n. You get that, which then clearly limits to 1 minus 0, or 1 plus 0, which is 1. So there you go. That limit is e. Here's another one. If we have, n plus log n over n squared, we can extend n continuously and apply L'Hopital's rule. If we do that, that gives me 1 plus 1 over n over 2n, which then by algebra is this, and those both go to 0, so the limit's 0. Right? You feel better about your day now that we're going through these examples, right? I do. And then here's one. If we had, oh, goodness gracious, natural log of 5 to the n minus the natural log of n factorial. Well, that sounds scary. But it's not, actually, because that's just the log of 5 to the n over n factorial, which we just learned that this guy goes to what? 0. Ooh. So what's log of 0? Like we don't talk about log of 0, we talk about limits of things. Well, fine. But the limit of a thing going to 0 from the right of the log of such a limit, it's minus infinity. So now, past this point, I have typed up 2 more examples for you guys, which I'll post. I actually worked out an example of an indeterminate power for you to look at. So I'll let you look at that. You know what I mean? Like 1 plus 1 over n to the end, like a 1 to an infinity kind of thing. You need to do something a little bit different there. So I will post those notes. You can look at them. But tomorrow, we are going to start a class. We'll be starting series. All right. So tomorrow is, we're going to turn the page and do the thing we'll be doing for like the whole next week. So thanks, guys.